All right, should we go ahead and get started? Okay. Welcome to Data Science Basics. I'm glad to see all of you and know that there are maybe 60 people who are joining us online. My name is Rebecca. I am a data scientist at the Commerce Data Service. I'm also a board member for the Data Community DC organization, which is a public organization of data science community groups. I'm also faculty at Georgetown School of Continuing Studies and at District Data Labs. My colleague here joining us is Bilbro, who is also a data scientist at the Commerce Data Service and a chair of mentors for the Women in Bio organization. So I've also included our contact information. If things come up after the class that you'd like to reach out to us about, please do so. We are hoping that in addition to teaching you about data science, that we will, this will be a forum to kind of generate some interesting ideas for projects that you might have for the work you're doing. So please reach out to us if you have ideas, questions. So goals for this class, so our goals for me and Pri, we'd like to give you some sort of groundwork understanding about data science. So this is not going to be a very technical class, this first class. The subsequent classes will sort of increase and become more and more technical as we go. But this will sort of be the foundations class. So we'd like to start by giving you a kind of foundational understanding of what data science is and talk about where the field came from, what the main skills and tools are that we use, talk about what a data product is, and talk about the data science pipeline. So for you, I would like you to think about your goals as being these 5 things. So first of all, be able to spot data science in the wild. So now after this class, what I'm hoping is that you'll be able to go out into your kind of routine life and be able to start thinking about the services and products that you consume and thinking about what kind of data science might be going on underneath the hood. I would like you to have an understanding about the data science pipeline and start thinking about how you might fit into the field of data science, where your strengths are in data and where you would like to grow. And you can kind of use that information to think about which other classes you might like to register for and what other work projects you might like to explore. Thinking about what sort of role data science might play in your work. And brainstorming, as I said, potential data science projects. So first of all, what is data science? The study of data. That's a great answer. I think that's a very good answer because it's sort of general enough to include a lot of different things. Are there other, other suggestions, ideas, study of data, other thoughts or examples that people might like to offer about what data science is?
Like right now, we might see data science specifically in the news, like around elections, right? So can you think of examples that you might be seeing either in your lives or just when you're looking at the news?
Nate Silver, good example. Yep, so Nate Silver runs a popular blog called 538. Show of hands, people who have heard about 538, read it religiously, have posted already on 538. You probably shouldn't be in this class. So yeah, that's a great example. Other examples that people are aware of, or other kind of general definitions of data science? Looking for patterns? Good. looking for knowledge within the data. Yeah, I like all of those answers. What I like about them most of all is that they're all really nice answers. I have heard a lot of, not nice answers. And so some of those answers that I've heard are that it's just rebranding. And I think that actually, somewhere in all of these answers, there's some kernel of truth, because in a lot of ways, data science is, borrowing from a lot of other traditions, academic traditions, that have been around for a long time. And so I do hear people say that data science is just rebranding. I also hear new methods, old questions. So, basically data science is just trying to solve, problems that we've always been trying to solve, trying to optimize things, trying to optimize expenditures, or, distribute resources, try to minimize costs, but that we're just doing it with new methods, maybe bigger, better computers. Alternatively, I've also heard people say that it's old methods and new questions. And do we have any statisticians in the audience? Yes. Okay.
And so it looks like some definitions that we got online kind of match that, right? Okay. We got like application of disciplined scientific principles to the understanding of disparate data sources, which is a pretty well written out answer.
Yep, that's good. Yeah, so I think for people who are coming from the field of statistics, I frequently hear some version of this answer, that it's old methods, new questions, that basically data science is just statistics, and all you're doing is asking new questions like, how can we use web traffic data to do this, so that, we're just applying, old methods to new data sets. Some people say it's something entirely new. I guess, to be honest, I feel like my opinion is somewhere, in the middle of all of those, and maybe it kind of fluctuates from day to day, depending on how good of a work day it was. So, does anybody watch House of Cards? Yeah. So I actually don't watch it, but I hear that there is a data science character on House of Cards this season. So I don't know, I don't know about this character, and I don't know how well this character is representing us. Hopefully it's not too bad, although I have a sense that most of the characters on the show are sort of questionable in terms of their character. We're both very nice. But what I think is interesting about House of Cards is this sort of tiny banner at the top that says a Netflix original series. So what's interesting about House of Cards is that it is a show that was engineered in response to people's preferences that they stated after watching television and movies on Netflix. So after you watch a movie on Netflix and you say, I love that, 4 stars, or you watch a TV show, I didn't like that, and you downrate it. So they used all of that data to determine what kinds of shows people liked. And they created a show that people would really like, and it worked. So that's data science. And I think that's a really cool application of trying to engineer and tailor products so that they will be the kind of the best product, the best service for the audience. Although I want to sort of rein it in a little bit because it's well and good to sort of make pop culture references to get the audience engaged, but I would like for you to also be thinking about kind of what data science means in our context for work and how we can use data science to better serve the public in our mission at the Department of Commerce. So the definition that I'm showing you now is actually from the chief data scientist of the U.S. Department of Commerce, who is also our boss, Jeff Chen. And his definition is, hey Stephanie, his definition is data science is the practice of transforming raw data into insights, products, and applications to empower data-driven decision-making. And there's some additional text there that sort of refines, where is the field coming from, and how is it different from some of the fields, some of its precursors. But I think that notion of transforming raw data into insights, products, and applications to empower data-driven decision-making is really the key here. And that's what I want you to kind of have in mind when we think about defining data science. So another thing that comes up when we talk about what is data science is this notion of what is big data and what's the difference between data science and big data. What do you think?
Data science is what you do.
Okay, so somebody said data science is what you do with big data, and I like that answer. Other suggestions? Yep. So we had somebody say big data is focused on different types of data, text analytics, so that's sort of the volume, the data ingestion, whereas data science is about the methods. So I like that answer too. I think that the way that I think about it is that the big data, became this sort of buzzword that was really, getting a lot of attention, getting a lot of play. You can see, The Economist has, a sort of front page article about the data deluge and how to handle it. And that's kind of how I think about it. Like, big data is the data deluge, and data science is how to handle it. We have this sort of Venn diagram to represent the 3 V's of big data, and I think that people have iterated on this and added additional V's in, like veracity, how good is the data. But the original 3 V's are volume, velocity, and variety. So volume for big data is how big is it, and we're talking on the scale of petabytes of data. And velocity is how quickly is it coming. So somebody in the audience mentioned streaming. And then variety, is what kind of data is it? Is it relational data? Is it unstructured data? Is it text data? Somebody else, had mentioned text data. So, but for the purposes of this kind of basics talk, I think the way that it makes sense to think about big data, small data, medium data is big data is too big to run on your laptop. Medium and small size data, you can actually run applications on your laptop, or you can run it on a Mac, you can run it on my laptop. I don't know about everybody's computer, but I think the thing that's sort of special about data science is that it's methods that you can apply using, basically just your home computer, and process a lot of data, maybe not petabytes of data, but a pretty high order. So where does data science come from? Yes. So yeah, so part of it is just this sort of demand for what are we going to do with all of this raw data? What are some of the kind of origins of data science? We talked a little bit about statistics, so we have some statisticians in the audience. In terms of other fields that data science kind of inherits from, what are some other fields?
Someone on chat said they felt like data science came from that broader need that erupted from big data.
Okay. In the audience? Yes, so actually that's a very good point. And it's not something that I hear people bring up a lot, but a lot of it is about kind of the industry that existed in marketing, trying to do direct marketing and do it as smart as possible. So data science definitely borrows from that field. Programming? Nobody has said, but we program a lot. Yes, computer science, data mining. Yes, Yes, yeah. So we use database design, database architecture, data management are all fields that data science inherits from. And what's interesting is to sort of see the reactions of people from those fields as data science starts to grow, which starts happening, around 2008, 2009, 2010. So Hal Varian, says that the next 10 years, the sexy job is going to be statistics, being a statistician, which I think people did not really take seriously at the time. But now we're 6 years later, and data science is the most exciting profession according to a lot of blog posts and news articles. So in a lot of ways, what he's saying, this idea of being able to understand data, extract value from it, visualize it, communicate about it, is really one of the hottest skills right now. Steve Lohr at the New York Times, said something similar around the same time, this ability to be kind of a new kind of statistician. So somebody who has the methodology of a statistician, but also really understands computers and can process, very large data sets. Mike Driscoll, in reaction to what Hal Varian said, says maybe we shouldn't be calling them statisticians, but these are people who, tend to have skills in 3 different areas, which include statistics, but also data munging, which is also known as data wrangling, and data visualization. And then this term data scientist starts to come up. Nathan Yao says, we're seeing data scientists, people who can do it all, emerge from the rest of the pack. So these are people who know statistics, they know about APIs, application programming interfaces, they know about databases, they know how to program. Here, this is much further back than before anybody else was sort of using this term. We have Ben Fry talking about kind of this combination of computer science skills, math skills, graphic design skills, and visualization skills. And does anybody know who Hillary Mason is? She's at Bitly. So she's kind of one of the celebrities in the data science community, but she kind of made this list of the 5 things that you kind of need to know, and so it includes a lot of the same things we've been seeing, this pattern of being able to get the data, clean it, do some data exploration, model it, and do interpretation or communication. And she starts to kind of frame this as a blend of the hacker's arts. Mike Lukaitis says data science is about building data products. So a lot of what this is sort of pointing to is that data science is kind of like a melting pot. And some people kind of directly talk about this as, data scientists are people who are like a jack of all trades. People who have a little bit of skill, here and there, and then when you put it all together, the sum is data science. And I really like the way that Venkata Strauss says this. He says that he is uncomfortable when people call him a generalist, because really what happened is he tried a lot of different things, and then one day he woke up and he was a data scientist, because his life sort of ended up adding up to this. And I think a lot of people in the field sort of feel that way. Drew Conway is talking about kind of how data science fits into academia, and is starting to say, the more importance that data starts to have, these skills, scraping, cleaning, visualization, start to become prerequisites for any academic research project. And Jeff Hammerbacher here is talking about his team, and talking about just the range of skills that any person on his team can engage in a given day, whether it's, writing Python code, doing hypothesis testing, implementing algorithms, spinning up Hadoop, and doing results communication. Other people have sort of just said that the term data science is like practical, and this person you might recognize. So our US Chief Data Scientist, DJ Patil, said that he and Jeff Hammerbacher, who was quoted in the previous slide, came up with the term data science because HR was being a pain. And this is back when they were both in California, and they were working on data science teams at Facebook and LinkedIn, and they coined this term, data scientist, because they were having so much trouble with HR trying to hire the kinds of people that they wanted to hire. So, is data science just a cooler way to say data analytics? What do you think? It won't hurt my feelings if you think that. Some people definitely think so. The president of the American Statistical Association says that she's expressing concern here that statistics is going to become subservient to data science, data analysis, data mining, and she wants people to kind of bring back focus on traditional statistics. We also see reactions from people in the field of operations research. Do we have any OR people? No. Operations research, data science borrows a lot of the tradition of operations research, and for some people in the field of operations research, they feel like data science is just rebranding. I think that those are interesting points. Here is a brand new article that just came out, and I'm not sure how many people have read this one yet, but this was in the New England Journal of Medicine recently. Jeff Drazen said, we worry that a new class of research person will emerge, people who had nothing to do with the design and execution of the study, but who use another group's data for their own ends, possibly stealing from the research productivity planned by the data gatherers, or even use the data to try to disprove what the original investigators had posited. There's concern among some frontline researchers that the system will be taken over by what some researchers have characterized as research parasites, to which all data scientists had a hearty chuckle. If you were following this whole debate on Twitter over the last few months, a bunch of data scientists were kind of tweeting out, "I am a research parasite," with a sort of gleeful attitude, including DJ Patil. And in fact, the editor-in-chief of Science Magazine wrote an editorial in response to the New England Journal of Medicine article saying, "I am a research parasite." So I think that this is a charged conversation. What is data science? Where does it come from? Is it new? Is it not new? And I think that it's useful to kind of be aware of that conversation as we sort of talk about what data scientists do and how it might fit into our work here in the government. But I also encourage having a sense of humor. Especially because now we are starting to have some conversation about, so you know that a field has sort of started becoming its own field when people in the field say that there are fake people and real people. Earlier this year, Kirkborn had put out an article on KD Nuggets that said, here are the 20 questions you can use to detect fake data scientists. We start to get into this zone where we're trying to differentiate people who are posers from people who are authentic data scientists, which is funny because, just a few years before, we're saying like, I had some skills in this area, I changed my mind and went into this other field, and then I tried this other field, and one day I woke up and I was a data scientist, to having enough legitimacy as a field for there to be fakers and then real data scientists. So I just find that kind of amusing. But this is why I say you have to have a little bit of a sense of humor. If there are real data scientists and fake data scientists, what are the key skills for data scientists? What kind of skills do you need? Programming and statistics. So I'm really glad you said that. And I think that, so somebody said you really need to know the data. And I think that this is sort of the flip side of the research parasites kind of thing. Domain expertise is really critical to good data science. And I think that that's why it's so important for people like you to take a class like this, because all of you are subject matter experts in some domain, presumably with commerce data, unless you just walked in here and you meant to go to the White House visitors area. But presumably, presumably all of you are domain experts in some data set or some set of data sets. And that is really critical to being able to do good analysis and modeling. And it's something that Pri and I encounter on a daily basis. We have a lot of tools at our disposal. We have a lot of programming tools, a lot of statistical methods, and a lot of algorithms that we can pull from. But you can't just generate data expertise in a domain overnight. And if you do projects, in Department of Commerce or anywhere where domain expertise is critical, you really have to partner with people who do have that domain expertise. So from my perspective, I'm less interested in saying, it's about being a real data scientist or a fake data scientist, and saying, let's all bring what we have to the table, whether it's domain expertise, whether it's your statistical experience, your programming experience, because all of that is going to be important in order to do effective projects. I very, very much like this quotation. So my whole kind of conception of data science has a little bit of a chuckle. So Josh Wills on Twitter says, a data scientist is a person who is better at statistics than any software engineer and better at software engineering than any statistician. And I think, do you feel like that accurately describes you, Pri?
It does. I like that you favorited it.
It's before they changed it to hearts. I took that snapshot, and then they changed it from the stars to the hearts. I didn't like that. But I think that a lot of people who are in the field of data science tend to see themselves kind of in a liminal space between things. So another way to sort of say that is by looking at the data science Venn diagram. So on the one hand, we've got people who have, math background, a background in statistics, maybe a degree in statistics, people who have domain expertise, as we said, who really know the data, and then people who, enjoy programming and have hacking skills. So when you kind of put those three things together, the overlap is data science. And so it's less about kind of being a specialist in one area, and it's more about having a little bit of everything. On the other hand, so just to sort of disagree with myself a little bit there, I think that thinking about the science part of data science is also really critical, especially, if we're going to use words like hacking, and danger zone, which we see, in this previous skill, like the overlap between hacking skills and substantive expertise is the danger zone. Without any knowledge of math, you are going to get in trouble very quickly. So if we're going to use terms like this and have a sense of humor, I think that we also want to be thoughtful about the fact that data science is about doing science. So it's about using the scientific method, doing hypothesis testing, doing repeatable research, things that other people can run on their machine and test to make sure it's valid. Those are really critical to the field, particularly in the context that we're in, because whatever we do, there's a lot riding on it, right? It's not about, just trying to make more money or to, build a cooler gadget. We are serving the American people. So it's important for us to think of ourselves as scientists. So there's this survey that you can take, actually. If you have a wireless device or you have your phone, I encourage you to go follow this link. And for those of you who are following along, I encourage you to take this quick survey that will sort of diagnose what kind of data scientist you are. It's really useful because in addition to kind of giving you a feel for where you fall, it can also kind of give you a sense of what you might want to work on moving forward, which skills you might want to develop, and also kind of what sort of team you might want to work with, people who can augment your skills. So actually, I think maybe we'll take maybe we'll pause and we'll see if there's, we can sync up with any questions that have come through in chat and give people a chance. Maybe we'll do, maybe we'll take like 5 minutes and give people a chance to do this survey. And we'll read through the questions that have come through the chat. And when we come back in 5 minutes, we can address some of those questions and talk about our results for this survey. Oh. That's like an inside joke. They get. So as people who are joining us via WebEx, as you get your answers, if you can, maybe you could put them in the chat so we can see what kinds of responses people are getting to the survey. You get any answers?
Yeah. We're getting a lot of data creatives with top skills in math or business or stats, some data researchers.
Okay. People in the room, anybody want to share what your diagnosis was? This is what I am. So the results, when you answer the questions, you end up with this sort of T-chart on the left-hand side, and on the right-hand side, this sort of barbell graph. So it evaluates your programming, stats, math, business, and big data skills, and then sort of says what your balance is between engineering and creative, and between business and research. Mine has changed a little bit over time. But yeah, my background is in math. I was a math major in college, so it doesn't surprise me that the green and blue are, the deepest in my stack, and that my business person bubble is small because I spent a lot of time in graduate school. What did you get, Pri?
I got my business person bubble is also small, but I got my biggest ones are stats and math, and my background is in like genomics and bioinformatics, so I have more in that Venn diagram. I'm more on the science and stat side, or yeah, domain expertise and stat side. So the hacking part is the newer part for me.
Okay. Anybody else in the audience want to share what they got? Okay. Yay, programming. Okay. Okay. So your T is strongly oriented towards programming. Yeah, I think this is a tool that a lot of people use. Some version of this when they're building data science teams, because when you're building a team, it's really a lot less about spotting the fake data scientists from the real data scientists. It's really about thinking about who will kind of bring together the skills you need in order to execute projects. So you need somebody who's a strong programmer, who has an engineering background. You need people who have algorithms experience, who can do predictive modeling. You need people who have domain expertise. Pri mentioned having expertise in genomics, biology. We had a couple other people mention domain expertise. So those are all critical. Other things that are sort of critical are having people who can talk about data. We have a whole team in the Commerce Data Service that's focused on doing front end. Actually, we have one of our front end representatives here, Radhika. You want to wave? So for people in the room, doing the communication part, making the user kind of be able to engage with the results of your work is a really critical part, so critical that we have an entire team of front-end engineers, in addition to having a data science team and a back-end engineering team. Just to kind of bring this home, I personally am not very interested in trying to categorize people as real and fake data scientists, and I'm more interested in, kind of thinking about, getting some self-awareness about where you fall as a data scientist, if you're kind of, more strongly oriented towards the business side, the communication side, the creative side, the programming side, the research side. If you're interested to read a little bit more about this, there's a free book here in the bottom right corner called Analyzing the Analyzers. So it's a O'Reilly Strata book, so it's free. You can just read it online for free. And it kind of talks about these different types of data scientists and how they navigate the work world. So if you are interested in reading a little bit more about that, I would suggest checking out that book. Speaking of books, the library actually has, and when you walked in, for people who are in the room, there's 4 or 5 books here behind you that are some of the kind of key resources that people use as they're starting to get into the field. And for people who are on the phone, I think you can check them out.
Yeah, even if you don't work in this building, you can check them out.
So yeah,
just reach out to the library.
Yeah, so if you're interested in kind of seeing what sort of books and resources are available, please do reach out to us, reach out to the library, and we can point you towards resources. Speaking of resources, so we've talked a little bit about what a data scientist is. We've talked about where the field came from. We talked about how it's different from big data. We talked about some of the skills that are necessary. But what about the tools? What kinds of tools do you imagine data scientists use?
Maybe think back to what you were asked if you knew when you registered for this class. Were there some skills that you had to fill out?
There's a ghost in the machine. I think I heard somebody say Excel. Did I hear somebody say Excel? Yeah. Well, just to validate you, it's there. It's in my slides. Excel is in my slides. Other suggestions of tools that data scientists use?
On the chat, we got Python and Ruby and Graph.
Yes, yes, and yes. Python, Ruby, and Graph. So Python and Ruby are both programming languages. I program mostly in Python, also in SQL. Pri is mostly an R programmer and also Python. Ruby is another very good language for data science and for developing. Other languages like, Julia are sort of starting to emerge.
Got some SAS.
We got some SAS, sassy. So for business logic and spreadsheet computation, the go-to resource that most of you have installed on your computer when you come to work is Excel, which is great because it's on your computer and you already have it, and probably a lot of you know how to use it from, learning in college or kind of using, doing trial and error. There may have actually been an Excel class offered a couple of weeks ago. Did anybody take that Excel class? So how was that? Was that good? So yeah, I think I think Radhika, did you take that also? The Excel at Excel class? No, that was, but what my understanding of that class is that it kind of showed you, you know, other uses of Excel that kind of go beyond some of the kind of basic things that you learn through trial and error, like things like pivot tables and stuff like that. Yes. One of the main benefits of using something like Python or R over Excel comes down to what the capacity is for Excel. So what is the max number of rows that you can load onto Excel before you crash it? $36,000? I've gotten beyond 36,000 before. Sorry. 1,024,000. That would certainly crash your Excel, for sure. Yep. Comparing different programming languages. That's a very good question. So, you know, if we're like, what's better if I'm going to learn Python, R, you know, Julia, Ruby? Well, obviously it's Python because I'm talking. I think it comes down to what kind of work you want to do with it. So Python is better for developing software. So if you're developing data science software and you need to you know, you need to like hook up to a database, and you need to hook it up to some sort of visualization tool, and you need to have like a front-end application running on top of it. It's hard to beat Python. If you're doing statistical computing, R is the best. If you're doing development, Ruby is very good. JavaScript is the best when it comes to, you know, building beautiful web pages that are interactive and communicate data. So it kind of depends on what you want to do. But yeah, Python. So how much does Excel cost? You guys didn't have to pay for it because you just walked in and it was on your computer the first day. It's not free. What about things like, do people use Google Docs or OpenOffice at home, on your home computer? How much do those cost? They're free. Say again? Okay, great. So tools for, what kind of tools do we use for mathematical and scientific computation? What tools do you use? How much does MATLAB cost? It depends on how much money you have, and they decide how much to charge you. How much do Python, SciPy, Matplotlib, Julia, R, etc. cost? They're free. What tools do we use for statistical modeling and analysis? Somebody mentioned Stata. We had somebody on joining us via WebEx mention SAS. Does anybody use SPSS? Yes. Okay. How much do these tools cost? They are not cheap. Most of them don't actually list a price on their website, which means it's a lot. How much does R cost? R is free. And it can do everything that SAS, Stata, and SPSS can do. Traditionally, what tools do we use for sharing knowledge and information? I'm thinking like books. How How much do books cost? Yeah, well, if you get them through the Commerce Library, then they won't cost you anything. But if you're buying them on your own dime, they can be quite expensive. You know, all of these resources that we have online, you know, read the docs, it's all free. What about database tools? What kinds of database tools do we use for data? SQL, okay. Excel? Please. Yes, okay. So do people use like Oracle or Access? Not anymore. SQL Server. How much does Oracle cost? How much does Postgres cost? Who said they use Postgres? How much does Postgres cost? It's free. Clearly, you know where I stand. Traditionally, what did we use for big data and doing distributed computation? Trick question. We didn't have traditionally big data and distributed computation, so we didn't actually have a solution for that. But now we use Hadoop, but also things like MongoDB, CartoDB, Cassandra, Neo4j, which are all free. What about tools for infrastructure and computing? So where did all the data live in terms of hardware? Sometimes on disk on your computer. What if it's like big though? Where did we? Servers. How much do those cost? All the servers. All the money. Have people here experimented with things like Heroku and AWS? How much do those cost? Trick question, not free. But close, I mean, relative to this one. So AWS is not free, but it's actually quite affordable. So for things like doing, you know, distributed computing and storage, it's hard to beat AWS. But even with all of the tools at our disposal, you still need your brain. That's the most important. So what I'd like to talk about next is sort of transition into the brain part and talk about what it means to think like a data scientist. And so what I would like to propose to you is this notion of hypothesis-driven development. So are there people who are familiar with hypothesis-driven development or test-driven development? Somewhat familiar? So what Barry O'Reilly says here is that practicing hypothesis-driven development is about thinking about the development of new ideas, products and services, even organizational change as a series of experiments to determine whether an expected outcome will be achieved. So this process is iterated upon until a desirable outcome is obtained or the idea is determined to be not viable. We need to change our mindset to view our proposed solution to a problem statement as a hypothesis, especially in new product or service development, the marketing we are targeting, how a business model will work, how code will execute, and even how the customer will use it. We do not do projects anymore, only experiments. So I would, strongly argue that when we are doing data science, we should be doing hypothesis-driven development, that we should be thinking about experiments, and that we should be open to the idea that sometimes experiments are not viable, so that, it's not about, trying to build something out of everything. Sometimes you're exploring a data set and you determine that there's not enough signal in the data set to predict something, and that's okay. So you keep this sort of post-it note in mind, that hypothesis-driven development is sort of these three things. First, we believe that this capability will result in this outcome, and we will know that we have succeeded when we see a measurable signal. And so when you're thinking about the projects that you are going to work on, I would encourage you to frame it in terms of these three things. So what is your hypothesis? What do you expect to see? And how will you know if the experiment has succeeded or failed? So in an organizational context, it comes down to these 8 things. Making data science work in an organization is a function of these things, and we need all of them to make it work. So the first is product ownership. So product ownership is the expert on the domain side. So this is somebody who, understands the data, has domain expertise, somebody who is committed to shepherding the project through the whole way. You also need to have some kind of theory of change, which is an idea of how the data science approach is going to improve outcomes at a very clearly defined decision point. So, when we change this one thing, we have this sense that it's going to have this sort of impact. So, kind of going back to this model, we believe that this capability will result in this outcome, and we will know we have succeeded when we see a measurable signal. So, in order to have data science work in an organizational context, you have to have this theory of change. So, in order to kind of make this change happen, you also have to have some sort of delivery strategy. And we're going to talk a little bit more about what these delivery strategies might look like in a little while. There's a lot of variety in what they can look like, and so when we get to the discussion on what is a data product, this is sort of what I'm thinking about. In an organizational context, a delivery strategy could be a data dashboard. Are there people who have data dashboards at work to kind of keep track of data? So that's one delivery strategy. New standard operating procedures or best practices, recommendation engines are all things that can make data science work in an organization as the delivery point. So number 4, domain growth potential. So what do I mean when I say domain growth potential? So there are a lot of fields who have a rich history of using quantitative methods to optimize. So the areas that tend to have the most growth potential are the fields that don't have that same history, don't share that same history. So a lot of social service fields, social scientific fields, qualitative fields, and a lot of the work that we do in the government tend to have a lot of growth potential because they're not fields where we have historically applied quantitative methods to optimize delivery, and success. You know, there are areas where measuring those kinds of things has been hard, because how do you measure something like innovation? Or how do you measure something like success? So, you know, a lot of the questions that we ask in the government are things that have been traditionally difficult to answer, you know, in quantitative ways, but data science can help make that possible. Another thing that you have to have in order to make data science work in an organization is data. I realize that we've made that number 5. Should probably be number 1. If you do not have data, or if you will not give it to me, I cannot do data science for you. So, you know, unfortunately, a lot of cases where, you know, asking data science questions could be really interesting, won't actually work in practice because, you know, the data just isn't there. Like we just haven't been capturing data to be able to ask those kinds of questions quantitatively. Sometimes this will point us to a means of collection. So sometimes you realize that you would like to be able to ask a certain question and you can't because you don't have data to ask the question or to support answering the question. So in that case, maybe that points to the need for some kind of tool for you to collect that data so you can later optimize based on those results. Data accessibility is also a must. There are data sets that exist but are not accessible, right? So what are some examples that you can think of data sets that exist but are not accessible? Say again? IRS tax records, great example. NSA, whatever they have.
I used to work at a place where most of the data was on an Excel sheet on someone's laptop, and that's why it was inaccessible to me, right?
So it wasn't top secret, it just wasn't shared. Mm-hmm. Okay. Yep. So yeah, like proprietary data for a company, import-export data. What about like, you know, census data? Census has a lot of data, a lot of very useful data. Does anybody here work for Census? So Census has excellent data. I'm glad that I asked that you guys work at Census. We love your data. Are there parts of Census's data that are not accessible? Yes. Like what? Right, so administrative records are not available, and why? Well, I have no idea. That is true. I've asked for them to get that. So somebody said PII. Do we have another suggestion? A lot of times, very granular data is not accessible because it can it runs the risk of uniquely identifying people or companies. The same is true with, you know, organizations like the Bureau of Labor Statistics, which has a lot of rich data and also cannot share a lot of that data because, you know, the fear is that right. So yeah, we want to protect people. We don't want people to be uniquely identified. We also don't want to disincentivize people filling out the census or filling out company information when the government comes and asks them questions. You know, if people are afraid to fill out the surveys, then we won't have any data. And so that's oftentimes the argument that's made for the sort of keeping some data, you know, not accessible.
There's another example of NOAA fisheries vessel data is not available. Is that true? Do we have NOAA?
And do we have any NOAA people in the room? So it's NOAA fisheries data is not accessible?
Fisheries vessel data, yeah.
Fisheries vessel data. Fascinating. What does vessel data mean?
I don't know. George Silva will tell us.
George
At the vessel logbook level, you don't have access to that.
So we don't have logbook data. So, I mean, I think, these are all things that we have to sort of grapple with as data scientists. We have to kind of, think about the fruit that we can reach, and think about how we can use that fruit to ask good questions. But in some cases, certain data sets are just not accessible. Data alignment. So the data also has to be appropriate to the hypothesis. Just because data exists and is available doesn't necessarily mean that it will help you answer the kinds of questions you'd like to answer. So, for example, a lot of times what we try to do is if we don't have a data set that directly addresses a certain question, what we look for are proxy data sets. So some of you may be familiar with the Commerce Data Usability Project. Have people heard of that? So one of the tutorials on the Commerce Data Usability Project is a tutorial about using satellite data to ask questions, basically questions about economic status, which I think is really fascinating. It's a fascinating application of this notion of using data proxy. So, if you can't ask questions directly, can satellite data, particularly for this tutorial, it's data about lights, nighttime lights. So when you look at the Earth at night from the sky, looking down, if you look at what areas have the brightest lights and the dimmest lights, what can that tell us about the economics of that area? What do you think? Say again? More lights, more money. So I think that is, that's basically the hypothesis that that they started with going into this tutorial is, can you use it as a proxy to ask questions about, economic success? And I would encourage you all to go and check out that tutorial to see kind of how they go about asking that question in a sort of data science way. Signal strength. So I said a little bit earlier that sometimes, having the data is not enough. So one of the things that we do as data scientists is looking at whether or not you can use historical data to predict future instances. And in some cases you can. In some cases, one of the examples that Pri is going to walk us through in a little while is about headlines in NIST data. So in some cases you can use historical data like headlines that have been published in the past to predict what headlines will look like in the future. In a lot of cases, historical data is not sufficient to predict future instances. And it's important to be able to use methods, statistical methods, to determine very early on whether or not it's going to be possible to make predictions based on historical data. Because if it's not, that's the stopping point. And then finally, appeal. So people need to be sort of excited about this. So this needs to be something that people are going to want to hear about. It needs to be a project that people are going to get behind, particularly, if we're thinking about domain growth potential. So we're talking about domains where these are not traditional methods. People, might be a little bit unfamiliar with what you're talking about. It might be a little bit scary. We've already we've heard, that people in traditional fields sometimes are threatened by some of the methods and questions of data science. and we've talked about delivery strategy, like how we are actually going to deliver this product to the users. So those things can be intimidating. We're gonna ask people to change things that they've been doing. We're gonna ask people to change established procedures. If you don't have appeal, if you can't get people excited about it, then it's not gonna work, right? So, I will put it to you to think a little bit about where data science might be applied in your field or in the work that you're doing. And I'm going to take another break so that we can check in with the people who are on the WebEx and see the kinds of questions that are coming up. But I would like you to think a little bit, and maybe even brainstorm with your neighbor about some ideas of things, projects that you could do, questions that you could ask. And I'm going to rewind to the hypothesis-driven development Post-it note, because what I would like you to do is think about your questions in terms of hypothesis-driven development, so that we're thinking about how we would use the scientific method to ask the question that you'd like to ask. But I would like you to kind of think a little bit about, the data that you have in your organization, some of the challenges that you have, some of the missions that you have that you think might be addressed with data science approaches. I'm going to go back to this Post-it note, and I'll give you a couple of minutes to think, and if you'd like to discuss with each other, that'd be great, and then we'll come back and I'd like to hear some of your suggestions.
The basic import-export data, and there's a bit of a lack of data on the trade barriers themselves. So the idea would be to try to use commercial databases on standards to try to look at trade barriers in a way that hasn't been done before, to try to use data science techniques with these large commercial databases. So which ones are you thinking of, like Hoover's data, like Dun & Bradstreet, or? So there's actually one called Paranorm, which is specifically done through international standards organizations and sold for lots of money. But has information on largely European standards, which is an issue with an area where we have a lot of trade barriers. I see. Very interesting. So it'd be kind of a project of mashing up, or lining up so trade areas and talking about using the standards as boundaries between potential trade, like between the United States and another country. Trying to figure out which standards are problematic in terms of U.S. exports, and looking at that in specific industries, which is how those standards are classified. Very interesting. Are there people on the chat who we should, maybe I'll grab the mic and then bring it up to you, Pri.
Okay, so over chat, one use case or one application of data science is the analysis of power usage draw to determine the best placement for server hardware. So they put the kind of in the note card form, right? So we believe that the analysis of power usage will result in less cost and or better utilization of power and cooling. And we'll know we have succeeded when we see an even distribution of power usage or draw and cooling throughout all the racks in the data center. So all the racks are roughly the same temperature.
Very cool idea.
And then another one is, we believe that using recent research results, radar measured rotational strength, and prior studies of conditional probability to issue tornado warnings will result in fewer false alarms. and we'll know we succeeded when the false alarm ratio falls below current values and remains consistently lower for several years.
That would be a really interesting one to test. I feel like that one, maybe it might require some simulation, since you can't sort of like hope for a tornado to come. But maybe there's some way to run like simulations to do some like predictive modeling. But yeah, whoever wrote that one, reach out to us and we can brainstorm a little bit together. It's an interesting idea.
Yeah, and then we have one last one, and it's for NOAA, for NWS, and they said they have the need to analyze how a prototype project of thresholds will lead to stronger preparedness actions among our core partners. A prototype project of thresholds will lead to strong preparedness actions among our core partners.
So this is you said NOAA?
Yeah, and NWS, National Weather Service.
Can you read it again? So we're thresholding.
Analyze how a prototype project of thresholds will lead to stronger preparedness actions among our core partners.
Okay, I think we might need to have a little bit more information about where the thresholds are. Like it's the threshold for when to send out like an alert or something, like a National Weather Service alert, or
Ooh, sorry. Now people are networking because someone else from NOAA was like, "Hey, share my name with that person."
Okay. Well, maybe we'll let you talk about
it
yourself.
is thresholds of hazardous events based on time and location.
Have they read the hail tutorial?
Oh yeah.
Maybe you could send a link to the hail tutorial. So there's another tutorial on the Commerce Data Usability Project website that does a little bit of this. There's an analysis of hailstorms, when they're most likely to happen and when they're most likely to be damaging. And there's like a complete walkthrough of the data ingestion, uses NOAA data, and could theoretically be used maybe as a basis to do some of that kind of questioning. So the next thing we'd like to do is kind of walk you through what it would look like to do a project like this sort of from beginning to finish. And I'm actually going to ask Pri to come up to walk us through this. But this is the NIST headline project that I referenced a little bit earlier. So she's going to walk us through kind of from this sort of beginning stage of, that starts with a question, all the way through, how you would kind of do the preliminary ingestion, what kinds of tools you need to have access to, what kind of initial analysis gets done, what does the predictive modeling machine learning phase look like, and then what do you end up with at the end. So I'll turn it over to Pri to walk us through that part.
Okay, so we kind of started the approach to this problem in part because we had a data science kind of hackathon, hands-on workshop where we were like, okay, we want to use commerce data and we want to have kind of an unlabeled data set to work with. So for NIST, I think we have some NIST folks in the room, right? Yeah. So there's, on NIST website, there's just kind of a big long list of all of the news pieces on all the articles that either they've published, and I think some of it is like things that other people published that are about NIST. But a lot of it is unlabeled in that you can't tell which component of NIST, what component of NIST this article applies to. So what we looked at NIST subject areas, of which there are 15, and said what would be really great is if, looking back at 2015 or 2014, we could tell generally if the publications, the articles, tend to skew heavier on certain subject areas versus others? Was there a year, in 2014, was it a big year for this particular subject area? And so we decided to apply a k-means clustering method. And the reason we picked that is because, you know, one website that has a big long list of the headlines as well as like the short description, like the first couple of lines from the news article. But when you click into it, there's no way to actually tell which subject area it applies to. So it's unlabeled. Versus if we had labeled data, we might be able to, an example of labeled data is, let's say we had patient data for 2014 for a whole bunch of patients that had with all their discharge dates, and we knew whether or not they died, right? And like what we were trying to predict is whether they would die. That would be labeled data because we have data that shows the kind of the answer for the question that we're asking, right? So we decided to do an unsupervised learning technique because the data wasn't labeled, and k-means clustering is an example of that. And so what k-means clustering tries to do is it takes your data and you're telling it how many clusters you expect to find in that data, right? And what we're using at that point is some domain expertise. For us, it was going on this website. But generally, like there's a domain expert that can say, this is like insight into the data and like insight into the question and the answer we expect. And what this method does is tries to cluster your data and kind of homogenize within cluster so that the amount of variation you see within the data points that fall in the cluster is minimized versus, you know, two different clusters within for two different clusters, the amount of variation between them is the most it can be. So the way that generally works is there are a couple of different methods, but with clustering there's a few centroids. For each cluster has one centroid, and they get placed. And there are a few different ways that can happen, but they get placed, and then each data point gets assigned to a centroid, to a cluster. And then that process kind of iterates a couple times to make sure that you're maximizing that between cluster variation and minimizing that within cluster variation. Right? And like understanding the actual method behind what the method you are employing is really, really handy because it also shows you all of the assumptions you're making about your data. So what we had to do, let's see what's on the next slide. All right. So if anyone has a laptop open or a tablet or something and they want to follow along, you can go to this GitHub page. It's github.com. That's a *C-Ying. And then open data DC is all with underscores between it. But all of our code is on there, and so are the slides we went through. And that might be a little bit handy because if you decide to run this code in Python, sorry, did you have? Yes, we can share the slides later. Yeah, and we're also going to share a recording of this later. But you could run this code for yourself, and then there's a slide that talks about kind of the ways to optimize your code, and you can kind of play with the parameters you pass in and see what breaks and what doesn't. But what we had to do was kind of start from, oh, right, you already had it up. Okay. Can folks see? So this is an IPython notebook, which basically means that we can have all of this kind of explanation and stuff, and then there are these little modules that actually have the code in them. And then if you were to get IPython, either on your personal laptop or on your work laptop, and this data is publicly available, so you can do it on your personal laptop, you could run each of these little squares and like have the code run in these little segments, so you can see what's happening at each point. So where we started was we actually had to scrape data from a web page, and let me scroll down a little bit. So that was kind of building the list of the headlines and the descriptions. We used actually a pretty helpful Python tutorial. I don't know where you folks are from the census folks on scraping, but it was a really helpful Python tutorial and a package that allowed you to scrape the website and taking a closer look So here's me passing the websites to our library. And then kind of creating a tree of all of the data that's stored in that website, on that web page, because so it would include everything like the little footer at the bottom that says last updated, whatever, or like the author. Like it would include all of the data that's on there. So what that meant is I don't really want all of that, right? I don't want to include the like last update date for the whole web page or like NIST at the top. So with a little bit of manual work, I had to go into the website, and at this component right here that I'm passing to it, I had to see, okay, so if I inspect, the headline component of the web page, where does it tell me that's stored? And then I could pass in to our package the location of both the headline, right, which is in this class, and here's the pulling out the text from it, and the description, which is in this paragraph, and here's the text. And then, I realize we're kind of jumping into code here, but I'm going to try to go through each line so that we can see what's happening at each stage and like what the code is trying to do. So I'm kind of creating a placeholder here and saying, okay, I got all of the headlines and all the descriptions. They're in each of this list of headlines, list of descriptions. Now, what I want to do going forward is combine each headline with this description so I can treat that as one like bit of data that I got, right? Like, because that is one article. So I create a placeholder for news, and I say, okay, for each headline in our entire list of headlines and for each description in our list of descriptions, I'd like you to take that little placeholder that I created, the news placeholder, and add on those two things together, the headline and the description, which means I'm relying on the list of headlines being in the same order as they got pulled, and the list of descriptions being in the same order as they got pulled, right? And because I'm making that assumption, and because I went in and manually told it where to pull headlines and descriptions from, the thing that I have it do right here is print out the last item in the list retrieved. What that allows me to do is see, okay, retrieving data from NIST. This component right here is what actually you see when you run that bit of code. And it says in the last item in the list received, we see this headline and this description. At that point, you would have to like go to the actual website to make sure those two things match up, right? Lots of like checking back. So great, we have news, right? We have all the headlines and descriptions together, but that's actually not particularly helpful for what we're trying to do, right? How do you go about clustering together words like strings? And what we really need is to say, okay, for each article, we need kind of a matrix of like what words were used in it, how often were they used? Because those are either the presence or lack of a word, and or how often it is used is how I imagine you're going to cluster those different articles apart. Because they might all say NIST in there, but only some might say molecular entomology, which is something I just made up. Okay, so this is where I'm using in this kind of TF-IDF matrix component. I can never remember what that stands for. Something frequency. Term frequency. Inverse document frequency.
How frequent is the term related to all of the terms?
Yeah, and the document here being our articles. So what gets created is kind of a matrix, a sparse matrix, because there are going to be some terms that were in some articles and not in others. We'll get a frequency for them. And also, what we need to do is toss out common English stop words, which makes a lot of sense, right? We don't want all of the articles to be clustered together for and, right? Because that's just something every article is going to include. And what we're going to see in this next bit of code is we also kind of log how long it takes to run this bit of code, which I think is really helpful to do. It's also a really good way to be able to tell how efficient your code is. because more than likely you are not sitting at your laptop letting this run and just watching it. You've probably gone in to get some coffee or something. So the first thing that happens is we print that we're extracting features from our training data set using that vectorizer, right? We quickly log what the current time is. I just threw a word out there, like our training data set. So generally, if you have, let's say you have a supervised learning problem. You have a data set where you know that you have a whole bunch of patients' data, for example. You have what their diagnosis was, how old they are, things like that, and then whether or not they died. If you had that data set and built a model off of it to be able to predict if someone is going to die or not, it would be really hard to tell if your model is any good. If you did not have a separate bit of that data set to actually test it on where you knew what the outcomes were, right? Because otherwise what you could do is build an amazing model that really, really well predicts whether or not someone will die for that data set, rather than something that's generalizable to like new data sets you get out in the world. So there are kind of general different rules on like if you have a big data set, how much you should put aside for training versus test. Sometimes it's more about like, sometimes it's about making sure you have enough for training as possible, and sometimes it's just that kind of the volume you're dealing with. But
12-fold cross-validation is the gold standard. 12 folds, break it into 12 pieces.
If you have enough data, that's great. But what you would do then, what that would allow you to do is say, okay, I built this great model that predicts whether or not someone is going to die when you give me all these variables about them. And then you take your test data set, run your test data set through it, and see how often it correctly predicted whether or not someone would die. So that's where like that training and test data set concept comes from. So kind of looping back to this. So we're passing along, we're creating that vector. We're taking the input, which is news, which is my wonderful bundle of all of the headlines and articles. I'm going to skip over that part a little bit, just to save time. And then we're saying that our stop words are English, right? Like there's kind of a list of all of the words that kind of commonly occur in all articles ever, so let's ignore those. And then we fit that. And then we take that vector and fit it to the actual news list that we created, right? So that allows us to like kind of calculate the counts, and then right here, there are kind of comments within the code that allow you to look at like feature names and things like that within your data set. And then finally, it kind of like prints out, like this is how long it took for your code to run. Here are the number of samples we got, number of features. So down here, this ran in like 3.5 seconds, which is great. Number of samples and the number of features. So that was kind of just all preparing our data. Like we haven't actually done any k-means clustering yet, right? We're just pulling out the data and putting it in a form that we can actually work with, that this method can work with. So for clustering, I don't know if it's cheating. It's being, doing your domain knowledge research, yeah. And you set the number of clusters to 15. We're going to call the k-means classifier and set an upper bound to the number of iterations for fitting the data to the classifier. There's actually a default number of times that this iteration will run, but we're going to actually talk about why we set an upper bound right there. And then and we're going to time the process again. Oops, sorry. So K is 15, right? We're going to put that out here. If you ever wanted to play with this code and make it your own with a different website, you would change the number of the number of clusters right there. And then we pass this. This is the method right here, the k-means method, and these are all the parameters we're passing to it. So we're passing the number of clusters. We're passing this parameter here, which is the method for picking where the centroids go, because there are a few different ways to do that. and then the maximum number of iterations. And then finally, and actually let me stop here. So for the maximum number of iterations, we actually ran this a couple of times. And if we jump ahead, you can see how this took 80 seconds. We found that the output we were getting when we ran it a different number, we iterated a number of times, was the exact same output, but it was taking a lot longer. And so that was like kind of tuning our model to like work with what we have, right? We don't want this to take much longer than it needs to if it's going to give us the exact same result. So we'll log the time, and then we're going to compute k-means clustering using the fit method. So we're passing that actual sparse matrix that we created, that we spent all this time up here building, to k-means. And let me actually jump to the results a little bit. So you can see how we were clustering our sparse data with k-means. Those are all of the values we passed to it. You might notice that there are actually more parameters here than there were in the one I walked through there. And that's because they're default. The method includes some default parameters that anytime you use a method, anytime you would use a function, you would actually go read all the documentation about it to see what it's doing by default and whether that works for you or not. But all of that runs by default. And it's done in 80 seconds. And what we get from our feature names is, here, this loop right here is taking for the 15 clusters, it's printing the number of the words that we're seeing in each cluster, basically, right? So these are the top terms for each of our clusters. So you can see how, and the order doesn't particularly matter, but you can see how for cluster 0, this one was about final house technology. I don't know what that one was about. But this one was forensic science. This cluster always emerged. It's about the Baldrige Award of Excellence program. But there's one in here. There's always one cluster whenever we ran this model that basically just said National Institute for Standards and Technology. Sometimes it said NIST, and then like one or two other words. But you can tell that that cluster isn't providing anything meaningful. All it's doing is showing you that there are a lot of articles that have the words NIST in it, which isn't particularly helpful. So when you try run, I do hope that folks will like try running this Python code on your own. But when you do, something you might decide to do when you run your own data through this is that when you see something like this, like cluster 1 has all of the words that absolutely mean nothing to anyone looking at this, because you of course know the articles have to do with NIST. What we might do at that point is actually change our stop words to include not just English, but to exclude anything that wouldn't have meaning to a domain expert, right? So we would probably have NIST, we probably have Gaithersburg if that's where NIST is located. I assume that's why that was in there. Any other words that a domain expert would be able to exclude from this process. So this is an example of like first iteration, right? You have a data set, you're trying to find something useful in it, you have a little bit of domain knowledge, you try running it, and then at this point you would optimize your model and see whether, one, it's answering your question. Like, can you actually tell if you were able to, if certain subject areas in NIST got published on more in 2014 or not? Are you seeing meaningful data, or are you seeing kind of junk because you haven't tuned your model to the data set that it's working on and to the question it's trying to ask? So, yeah, let's do questions.
We have one question on WebEx. Is this data mining?
So there's a component of it that is kind of scraping the data that we didn't get in a wonderful like API or anything like that. But we are scraping part of our data to be able to run this model, which is just this part right here.
Yeah, so for the gentleman interested in scraping, the go-to Python library is called requests. So actually, if you scroll up a little bit, here are all the import statements. So you can see that the The second library that we import is called requests. That is sort of that's the best Python library that I know of for making calls, making web calls. It's built off of two older Python libraries called EarlLib and EarlLib2. So when you look for tutorials that are a little bit older, you might see them using EarlLib or EarlLib2 instead of requests. But request is kind of the most powerful Python library I know of for making web calls. And you can see that we're using LXML, the HTML method from LXML to do the parsing of the web page. There's actually another Python library called Beautiful Soup that you might want to look at for HTML parsing that I use a lot in my work. Other questions about this? I can walk around the microphone.
You mentioned something about the terms of service for most of the websites, and I hit some roadblocks there. Out of basically, I didn't have enough knowledge what to do and what not. Do websites provide these things upfront? Do they frown upon or sort of ban you?
So in my experience, there's a lot of variation between websites. One of the advantages that we have here is that we are scraping our own web pages. So that's nice because we sort of encourage research parasites. But you know, one of the sort of hot things that people like to do now is scrape Twitter data, which is actually incredibly easy to do. With like a little bit of Python, you can get a whole bunch of Twitter data. You have to register for an API key and a token, like a developer key. But they put like, you know, limits on how much you can pull at a time. So they rate limit you. I think, I don't know, it's 1,000 per day, 5,000 per day, or it's either 5,000 per day or the other is like so much every 5 seconds or something like that. So basically what that means is that if you need a lot of data, you need to start early because they're going to slow down how much you can actually get per day. And it's not because they don't want you to have data in the case of Twitter. It's because you're slamming their servers and the servers are like sleepy and you're like, oh, stop. So in the case of like Twitter, they want you to use the data. I mean, like using Twitter data makes people want to use Twitter more, so it's good for them. So in the case of something like Zillow or other web pages like LinkedIn that have a lot of data that people would like to scrape, the terms of service are different there because you know they're more protective of their data. And so I would just encourage you to like actually read the terms of service or you know, we can talk about it and kind of think about proxies. You know, sometimes there's a way to kind of think about something that's not actually the data you want directly, but is something similar to it that can help you answer a similar question. But yeah, I would say strongly encouraged to look at the terms of service. I definitely have gotten blocked before for sending too many API calls. It's definitely happened to me. Other questions?
This is just, before this, like this is a really interesting example, so thank you for sharing it. I was just wondering, so historically, it's been a couple of years, our CIO's office was a little bit nervous about letting staff download open software and open source software. And I didn't know if you guys had any resources for, you know, since, you know, kind of the workaround for our office is we've actually spent a lot of money on software that is like, you know, that's certified and all that stuff. How did you, I mean, obviously I can imagine your organization is going to be should not be putting up too many roadblocks to download it. But do you have any tips or information that you can share with bureaus?
That was a very good question. So I will say that that is like a very common problem, not just here at Commerce, but kind of across government and just across organizations. And the reason is like a really practical reason. So like if you're IT, you know how to like fix a certain set of problems with computers. And for the software that your organization has purchased, you know how to call the IT people who provide service for that account, right? So if it's open source software, who do you call? Like if somebody breaks their Python, like who do you call to fix the Python?
Rebecca Bilbro.
Oh no, that's on record now. Bugger. Well. So that's sort of the problem with, open source software is that, from an IT standpoint, it's really hard to manage and maintain. It really has a lot less to do with, security concerns, in my opinion, just because, those are things that it's just a process and you go through and you vet it and make sure there's no malware. And so there's kind of like a process for doing that. What's really hard is like, maintaining and servicing people. But what I can tell you is that my understanding is that Python and R are both on the list of things that are currently under review for all of Department of Commerce, and that within the next 3 months, there'll be approval for everyone to be able to use them. So that's my understanding from the Deputy Chief Data Officer. So. Yeah. We've gotten a lot of questions about this because a lot of the courses we're going to be teaching are in Python and R. And if your agency CIO is, skittish about that, I can appreciate how that would cause a little bit of conflict. And the idea is not to cause conflict; it's just to kind of come up with a system to sort of show that these are normal tools, and that. It's very unlikely you're going to break your Python, or if you do, you can call Rebecca Bilbro. She will come and try to fix it for you. But yeah, that's a very good question. Other questions before we move on? I should check the internet. Tag. Anybody else who's any other questions that came through chat that we should address before we move on?
There was a question that says, is the mining done by vectorizing and clustering? Right, and the way I kind of look at this particular bit of code is that we have 3 components, right? There's like pulling the data we need. There's putting it in the kind of shape that we need it. Right, that's the creating that vector, that matrix, and then there's the actual machine learning component, which is the clustering. Mm-hmm. Mm-hmm.
Yeah. So the question was, is the data mining the vectorizing and the clustering? So yes. Yes, the answer is yes. So what's going on with the vectorizing? So if you think about it, like. When you do machine learning, you can't really do machine learning on words because the computer is expecting numbers. And that's sort of like a very gross oversimplification, but just like go with me on that. So let's say we have to figure out how to do machine learning on words. How are we going to do that? You have to figure out how to make the words into numbers. And the way that we do that is by vectorizing the words. So if you have the word dog, the way that you would vectorize that is say, I've got one letter that's a D, one letter that's a O, one letter that's a G. And so for each of those, you create sort of a map, like a numeric map to the word. And then if the word dog appears in a document like 10 times, then you can numerically represent that too, right? So that's called vectorizing. So in a sense, that's data mining because we kind of create these maps between text and numbers, and then we use clustering to look at those numeric representations of the text and kind of figure out how proximal they are to each other. So how close is this document that has the word dog in it 10 times from this document that has the word dog in it 1 time, or this other document that has the word cat in it, or dogs, or something similar, right? So what we want to do is determine how proximal they are to each other, or a little bit what Pri said is that the flip side of that is that we're trying to decide how distant they are from each other, and that helps us define these clusters. So I'm not sure if that answers the data mining question, but that's sort of my take on it. Were there other questions on the chat before we move on to the next part?
No more on chat.
No more on chat? Hope we got one more in the room. You want to say it and I'll just repeat it? This is totally unsupervised, but we will be talking about supervised methods shortly, so stay tuned.
And what makes this unsupervised is that we could not, because I suppose maybe we could have gone and done it manually, but we did not know what subject area each of those articles actually applied to. So that's what made it unsupervised. And we couldn't pull another data set that had articles and and they were labeled and said, what subject area applied to test our data against, for example.
Yeah, it's a really good question because I think a lot of people, when they're new to machine learning, are kind of like coming in with the question of like, what's better, supervised or unsupervised? Like, what's better, classification or regression? But the truth is that a lot of the time it's largely not up to you. It's sort of what is the data, and then the data determine, what the methodology should be. So if you have labels, so if you know the answer already, like for these headlines, like if we already know for each headline, if we already know what the theme is, and it's labeled with a theme, then we would probably do classification, which is a supervised method. So we'd say, all of the headlines that are in this kind of bucket have the same label. So then we can predict, with future headlines that aren't labeled, we can guess what bucket they belong to. So somebody who does public affairs probably would love something like that because then you don't have to manually bucket everything. You can just create an engine that makes predictions based off old data. So that's an example of how, you might use supervised method if you had labeled data. But in this case, there weren't labels, so you have to use these unsupervised techniques that just look for like bubbles in the data. So, data points articles that are similar to each other and are different from other articles. And then you can kind of dive into that cluster and say, what is it that's, like the human part is then looking at the clusters and saying, what is going on in this cluster? Like what do they all have in common? Why are they all like close to each other? And then you, the human, can put a label on that. And then moving forward, maybe you could do supervised, classification, based on that. Does that answer your question? So, what is a data product? I feel like I gave you this answer earlier, and I told you I was going to ask you about it later. We'll see if you actually remember. Yeah, what's a data product? What do you think? Something that answers the question? Okay. Other answers? Yep, something that like empowers data-driven decision-making. Other suggestions? So when the term data product first started coming up in conversation, this is Hillary Mason again, and I showed you a quote that she from about 5 years ago when she was sort of talking about data science as being a combination of the hacker's arts. So she's one of the first people who starts talking about data products, something that is a byproduct maybe of data science. or parallel to data science. So what she says is that a data product is a product that's based on a combination of data and algorithms. So I like this definition because I feel like it does a good job of sort of responding to some of the questions that we had in the beginning about what is a data scientist, where does the field come from? It's a combination of, statistics and programming. So I feel like this is sort of responsive to that. But there have been some iterations on this since what she first said that I think are worth kind of looking at. So here's Mike Lucadis again, who says, a data application acquires its value from the data itself and creates more data as a result. It's not just an application with data, it's a data product. So what we're starting to get here in Lucadis' definition is the notion of an engine, something that has sort of perpetuates data. So it takes in data as the fuel, and it generates more data in return. So I think that this is starting to get a little bit closer to where we tend to think about data products, because, what we want to sort of move away from is the idea that data science is about taking in data, doing analysis, and then kind of writing a report that goes on somebody's desk and is sort of like, that's all. We want to sort of be able to generate something that has utility, and that utility is going to be more data, more information. So this, I think, is my favorite description to date of what a data product is. So this comes from a blog post on the District Data Labs blog, and the name of the post is The Age of the Data Product, I think. So the author, Benjamin Bangfort, says data products are self-adapting, broadly applicable economic engines that derive their value from data and generate more data by influencing human behavior or by making inferences or predictions upon new data. So to me, this feels like the most sort of comprehensive and accurate description. And it really, again, it has that idea of taking in data as the fuel and generating more data at the end, so that you can have this sort of iterative process. So if you'll remember, one of your goals for this class is to be able to spot data science in the wild. So now that we've sort of talked about some examples of data science, what data science is, we started talking about what a data product is. What are some examples that you can think of data products in the wild? So we had somebody say the way that Gmail sorts mail into the categories, like your primary inbox, promotional stuff, social. There's a social category, and you can create your own categories. That's that's a great example. So they're using information about your past sorting behaviors to build there's a classifier, a supervised classification technique underneath the hood that's making decisions, making predictions about new emails that you get that you haven't sorted yet, and it's making guesses about where to sort them. So that's a great example. Other examples?
A website, one dot per person based on the census data. So it's essentially a map of US with data from the census data. Essentially looking at different economic and social factors. It's probably on Washington Post or New York Times.
Huh.
And essentially, there's a dot per person, and you can see the population densities, the racial mix-up, the economic mix-up. So it's very cool.
Oh, interesting. So it's like, it sounds like it's an ingestion of a bunch of census data, and then they surface it on a map so that you can kind of zoom in filter. That's very cool. Yeah. So I think it depends on what you mean by data in return, like generating data in return. So, on some level, it's really just presenting data that already exists. But I haven't actually seen this website, so I'm not sure. It's possible that there is some generation or some calculation that's happening in addition, that is kind of reacting to incoming data in addition. But based on your description, it sounds like it's it's a data visualization. Other thoughts? Yes. Very good. Recommendations. So what are some kind of recommendation systems that you engage with in the wild? Yeah.
Netflix.
Amazon, Google, Netflix, all very good suggestions. So those are all recommender systems that use data about you, about your past preferences, so your search history, Google uses your search history and your location to help tailor the results. So actually, I don't know if you've ever noticed, but if two people Google the same phrase in two separate places, do they get the same result or a different result? It's different. Yeah, and that's by design. It's not just like, oops. It's by design because they want to tailor the result to the location that you're in. So if you Google Georgetown from Georgetown campus, and if you Google Georgetown from like Sri Lanka, the results, the order of the results will be different. Actually, that's my hypothesis. I haven't actually gone to Sri Lanka and Googled Georgetown, but yeah, recommender systems are an excellent example of data products. Some of these are ones that we've already identified. So Google is a great example. It uses your location, your past search history to help tailor the results that you get. LinkedIn has a recommender system that helps propose to you potential connections that it thinks people it thinks that you might know already based on machine learning algorithms. This flight recommender tool. Does anybody have a Nest in their home? No, because we work for the government. But Nest is a way of tailoring. So it's a thermostat system basically, but it learns about your heating and cooling preferences over time, and then it tailors them. It tailors the temperature of your house to your specific preferences. Yes, part of IoT, Internet of Things. Does anybody have one of these? Maybe you have a cooler color. I put the black one up there because I was trying to be gender neutral. But I don't have one. Probably should. But this is a Fitbit. And a Fitbit is another example of a data product. What data is it taking in? What's the fuel? Right, and what is the data that it generates in return? Yep. Yeah, I mean, I think it can do, I don't actually have one because government, but my understanding is that it generates data about, it gives you information about you. So it tells you, how many hours a night you sleep, and it's guessing that based on how much you move at night. It tells you how hard you were working on, on your last bike ride compared to the previous one. And I don't know, does it make recommendations? Like, get out of bed right now, you lazy piece of crap? No, I don't know, probably not. But maybe like, it could play like motivational music to encourage you. So anyway, this is another example of a data product. Here's an example of a kind of a different kind of data product that makes decisions about utility based on the energy grid. And here is an example. that some of you may have heard of. Does this ring a bell to anyone? So this is a data product that predicts where fires will start so that firefighters can go to those locations and address hazards before fires actually occur. Mm-hmm. Yeah, actually, so somebody in the audience, for the people on WebEx, somebody in the audience mentioned Google Flu, which was an attempt that Google made to predict flu epidemics from year to year. And the first year, their predictions were very good. The second year, their predictions were very bad. And actually, if you're interested in that, I can send you an article that sort of talks about why their second year predictions failed so badly. But this example, this one, so this is an article called How Data and a Good Algorithm Can Help Predict Where Fires Will Start. This is a data product that was actually built by your very own chief data scientist here at the Department of Commerce, Jeff Chen. So this is something that he did before he came and joined the team here, that he helped develop the system that would predict fires for the New York City Fire Department. And it was incredibly accurate and ended up predicting a lot of fires and helping prevent them. So somebody mentioned Netflix. Can't remember. It was when we were talking about recommender systems. So Netflix actually put out this challenge a couple of years ago, and they challenged, the community to improve the accuracy of their predictions, to make the recommendations that they give to viewers more accurate, about what kinds of movies that they would like to watch. So what they did is they put out this large data set, it was about 500,000 people, and how they had rated 18,000 movies. And you have to, come up with predictions for movies that those people haven't seen based on movies that they have seen, and also based on the ratings of people who have seen those movies and how similar or different the people are. And the first team to win, or to beat Netflix proprietary algorithm was going to win $1 million. So when this actually happened, there is a data mining professor, Anand Rajaraman, who actually has a really great blog, if you're into data stuff, called DataWaki. So he gave this challenge to his students. And I think he did it after the challenge was actually over, because he wanted to know if his students could beat the people who won the challenge. And he talked about two teams of students who attempted this challenge. The first team came up with a very sophisticated parameterized algorithm using the data that Netflix provided. The second team used a very naive, simple algorithm, but they added in additional data beyond just what Netflix provided. Specifically, they used data from IMDb. Does anybody ever look at IMDb? Okay, so you know what I'm talking about. It's like where you go to get information about movies. So IMDb has data not about, not just about which movies are liked and disliked, but about, about like, the genre of the movie, the characters, it has names of actors who are in it, and those are all things that probably somewhat factor into your decision to watch or not watch, or like or not like a movie. So, guess which team did better? Yeah, by a lot. And they actually got very close to the results of the team that won the $1 million. So the lesson from this the phrase that we use in data science is that more data usually beats better algorithms. So, you know, you can tune your algorithm as much as you like, but in the end, the hazard that you're likely to run into is what's called overtuning. So when you overfit your model, what you're doing is you are relying too heavily on the data that you have without generalizing enough for the data that's to come. And the way that you can preempt that is by adding in more data. And so, you know, some of you are already thinking about this. So we heard from the people at Census who are saying, you know, we need to ingest other data sets to see, you know, what potential vulnerabilities are. So we're not just going to use census data, we're going to look for other data sets, and that when we merge those together, that will actually, you know, give us a lot more information and help us do much better prediction. And there was somebody else in the audience who talked about ingesting other commercial data sets about trade, you know, to merge in with the information that we have internally about imports and exports. And I think that you're really on the right track there. You know, it's nice to be able to come up with like beautiful models, beautiful algorithms, but they just can't compete with additional data that can add richness to your model that can allow it to predict the future. So we have about 20 minutes left. So in the last 20 minutes, I would like to run through quickly what the data science pipeline is. So these are sort of the phases that we go through. And you've already seen this a little bit with the tutorial that Priyanka walked you through. You know, basically when we visualize it, we tend to do it in thinking about these 5 stages. So we start with data ingestion. We move to data munging and wrangling, which is also called data cleaning. Then we move to computation and analysis, which is sort of like doing preliminary exploration and modeling. And then you move to production modeling and application, which is like the heavy-duty machine learning part, and then to reporting and visualization. And as you'll notice, there's another arrow that goes from reporting and visualization back up to data ingestion. And why is that? Right, because what we're doing is building data products. And what's the definition of a data product? Right, so it takes data in and it creates data in return. And so what we want to do is see a feedback cycle, right? So we want to get better over time. So data ingestion. This is sort of the, you know, using Python requests and Beautiful Soup to go out and make API calls, gather the data, you know, where are we going to go get it? What is, you know, how much data are we going to get back? You know, this is when we need to start thinking about where we're going to put that data, where are we going to store it, so that it'll be secure, so that we'll be able to go back and do analysis. The next step is data munging, wrangling, cleaning. So this is the stage where we go through what we've collected and clean it up. This phase is sort of popularly maligned, let's say, as taking 80% of the work of a data scientist. Yeah, data is never in the right shape. Yeah, it's never in the right shape that you need in order to do the work you need. It always takes cleaning. It's always like the fields that get you are like the date time fields, where date time is represented in 12 different ways and you have to use regular expressions to clean it up. So I do have a class on data wrangling with Python and pandas that's coming up in a month or so. So if you would like to hear more about that, please sign up for that class. So next is computation and analysis. So this is the phase where we need to kind of use statistics to do some preliminary exploration of our data and understand, what kind of model we need to build, where we might have errors that we need to account for. This is a place where we can do preliminary regressions to decide if prediction is even possible. So this is maybe the stage where if we were going to do unsupervised learning, this is where we would decide to use 15 clusters instead of 10 by using things like histograms and key counts and stuff like that. The next step is modeling and application. So this is the stage where you are using either unsupervised or supervised learning. If you're using supervised learning, you're using either regression or classification. If you're using unsupervised learning, you're using clustering. And some of the names of the models that are kind of common that people probably have heard of are things like logistic regression or linear regression, ridge regression, decision trees, especially random forest is really popular right now. Support vector machines, SVMs, are really popular. KNN, which is what we saw, K nearest neighbor, Bayes and naive Bayes. Bayes actually is one of the kind of very traditional statistical techniques that's implemented now for a lot of recommender systems use Bayes under the hood. There's also another kind of machine learning that's not represented here that I feel like I should say, just in case any of my teachers are listening, called reinforcement learning, which is where you set up a system of reward or punishment, and the data sort of try to maximize reward or minimize punishment. So finally, reporting and visualization. This is the part that's often overlooked, but it's critical. A lot of times, kind of putting the initial data product out there will result in a chance to get labels. So I explained, with the clustering example, we have the clusters, we look at those, and then we need a person to look at those clusters and say, this is what that cluster means. This is the cluster of articles about this topic. A machine can't do that with, with the unsupervised learning technique. So we call that active learning. So we have an actual human being going through and labeling it. So that visualization stage is critical to being able to move forward with that kind of model, or else you're just going to, cluster and then it's sort of done. So you need domain experts to go through and help you label that data through active learning and visualization stage. So, in our last 13 minutes, I want to talk a little bit about where to go from here. One thing that I would like to pitch to you is checking out the Commerce Data Usability Project website. So the URL for that is here. It's www.commerce.gov. /data usability. So this is a page that I've referenced, 4 or 5 times now. One of the really nice things about this is that each of the tutorials includes all of the code that you would need to execute the project, and you can just fork it, using your GitHub account. You can, open it up and play with it. And experiment and try different data sets and iterate and optimize, like Pri said. So I think this is a really great way to start seeing some concrete examples that actually use Commerce Department data. So you can start thinking about how this might make sense in your work context. I also encourage you to check out our GitHub page. So people who are familiar with GitHub. People who are not familiar with GitHub. So we've got an enthusiastic waiver. So I don't know if you know, but I will be teaching a class on GitHub coming up in 2 weeks. So I hope to see you there. So GitHub is basically it's a website, it's a web application that hosts code repositories. So these are code bases. For programmers, it's kind of like your portfolio. So if I was going to apply, to a job to be a programmer for your company, you would go and look at my GitHub repository and see if I'm really good at programming. Because you can look through all of the open source code I have, and I think I just implicitly invited all of you to go look at my GitHub account and see if you think I'm really a good programmer or not. That was maybe a mistake, but one thing that's nice about it is that it's also a really good forum for collaboration. And so at the Commerce Data Service, we use GitHub as a way to collaborate with each other. So you can post code that you're working on, and your partner, like Pri, could check out my code, iterate on it, and check it back in. And then I can look at what she's changed and say, huh, that's such a better solution than the one I came up with, and I can merge it into my version. And so together, we can work together to make the best product possible.
How should we go about developing tutorials to contribute to the Commerce Data Usability Project, and how do we submit them?
That is an excellent question. And I think that the protocol is to send an email to Star. His email is sying@doc.gov. So sying@doc.gov. So I think the protocol is to send him an email, and he will respond to you with some sort of more information about what's involved in submitting a tutorial. We are absolutely accepting proposals for tutorials. We're happy to help you suggest data sets, although if you're in commerce, you probably already have some ideas about interesting data sets. I think there are three requirements, which are, it has to be an open data source. There has to be a commerce data set, open source tools, so you can't use like SPSS that nobody else will be able to run on their computer, and it has to be visually arresting.
I think there's a count for like the number of visualizations it has to have. I don't know about the arresting.
That's what Star always says, so I just feel like I have to say it the way he says it. But if you have more questions about that, reach out to me or Pri or to Star, and we can kind of get you pointed in the right direction. I want to take a quick moment to thank, he's not here, but I kind of feel like he's always listening. My teacher, who taught me everything I know about machine learning and data science, Benjamin Bengfort, he is a PhD candidate right now at the University of Maryland, and he's a data scientist at District Data Labs. He's also faculty at Georgetown University, which is where I learned from him. And these are mostly his slides. So thank you, Ben, for helping. And I would strongly encourage you all to follow him on Twitter if you are interested in learning more about data science. And you can check out all of his code on GitHub, which is much better than my code. He is really, he's been in the field a long time, and he's really terrific. So that's Benjamin Bengfort. Oh, sorry. You want to take a picture? Okay. So other things you can do moving forward. I want to point you to some resources. These are all things that are free. The two go-to websites that we use when we don't know the answer to something are Stack Overflow and Stack Exchange. So like, if the question is, which Python library do I use to make web requests or API calls, it would be Stack Overflow or Stack Exchange that would give you the answer. Coursera, probably most people have heard of that. They have free classes, and a lot of them, a lot of new ones around data science and big data. KD Nuggets is a blog that a lot of people in data science read and follow. District Data Labs is a blog that has data science tutorials and lessons. And Benjamin Bankfort, my teacher, blogs there regularly, has a lot of really excellent blog posts with tutorials and free code bases and stuff that you can use to do what you would like to do. I actually also have a post published there that you can check out if you would like to. It's about Introduction to Machine Learning, or you can take my machine learning class, and I will teach you those things also. Also, Data Community DC is a great resource for people who are here in DC, which I assume is everybody in the room and some of the people on WebEx. So if you are interested in kind of getting involved in more data things, I would encourage you to get involved in the community. There are a bunch of like free meetup events. They offer like free pizza, so you go and like you eat pizza, and then there's a lecture about how somebody used this algorithm to do this thing at their job. Or you can learn about data visualization, about data wrangling. There are meetups for people who just use R, for people who just use Python, for people who use both. So I would strongly encourage you to check those out. It's not just because I'm a board member at Data Community DC. Books to read. So I mentioned that the research library here has stocked a lot of really terrific data science books, and you can see those on display here for the people in the room. For people who are not in the room, you can also check them out. So you just reach out to the Commerce Library to find out how you can check them out. Here are some other examples of really excellent books that you might be interested in reading. I strongly recommend the O'Reilly books for data science topics. Other resources out there, MIT has a bunch of open courseware. It's a little bit like the Coursera model, but they have everything from algorithms and linear algebra to statistics if you feel like you need a refresher. This is my blog post on machine learning with Python on the District Data Labs blog. The map that you can see up here in the right-hand corner is the scikit-learn machine learning map. It's called Choosing the Right Estimator. What did I say? Scikit. Oh, right. Scikit. So scikit-learn is like the best library in Python for doing machine learning. There are a couple others that are pretty good, but scikit-learn is really incredible. It's incredibly powerful. Everything that you saw in Priyanka's tutorial is done, all the machine learning is done with scikit-learn. And if you take my machine learning class, I will teach you how to use it. Or you can check out my blog post on District Data Labs and you can read, get a little preview. Binge watch machine learning. So this is a bunch of data school.
Statistical learning classes, basically, that is kind of like MIT OpenCourseWare.
Okay.
And they use a lot of R, though, if you're an R person.
And then Introduction to Statistical Learning in R. So we'll be circulating these slides to people who are registered for the class, so you can check out all these links later. And I gave you our email addresses earlier, but I wanted to, now that I feel like I've made an argument for you actually wanting to contact us, hopefully, I'm giving you our email addresses again. Be happy to talk to you offline and talk about projects, brainstorm together. And 3 minutes to go. If there are any questions, I'd be happy to answer those. Are there questions on the WebEx? Questions in the room? Yes. The question is, how do you know if you're registered for a class?
Email on Friday that had instructions for this class. Did you? Yeah, you should get an email. I don't know if you'll get a confirmation email right away, but we do have the list of all the folks that signed up.
Does that mean you're going to take more classes? Yay! All right, other questions before we wrap up? This has been 3 hours of absolute pleasure. I'm so glad that you all stuck it out this long. This is a little bit of an experiment, so thank you. And I hope you enjoyed yourself. We enjoyed meeting you and hearing your ideas and your questions, and I hope to see you around for the future classes.